Before we go to the deep neural networks, I want to spend maybe another 10 minutes to talk about this Sift feature and the Hawk feature. They are used very often before the age of deep neural networks. The Sift feature is actually built on top of the convolution concept that I have just talked about. So what do I mean by Sift feature? The name stands for Scale Invariant Feature Transform. It was proposed by David Low in 1999. And the idea is actually very simple. It says it's convolve the image with a second order derivative of Gaussian. Okay, so what is a Gaussian? A Gaussian has a shape like this. So the first order derivative of Gaussian would be like this. And then how about a second order Gaussian? Well, it will be like this. Okay, so let me ask you, if you convolve your image with this Gaussian, this is the first order derivative of the Gaussian, what do you get? Well, it's sort of like the 1 minus 1 idea I just illustrated. So you should expect to get some kind of edge by using this Gaussian filter. If you convolve with this guy, what do you get? You're getting like a blob, okay, like a circle, all right? So if I can change the scale of this blob, okay, I can change the scale of this second order derivative with some systematic way, I should be, in principle, to get a set of blobs in my image. Okay? So keep this in mind. This is actually what the Sift is used for, is to get the blob of the image. So say that, okay, in this image, these locations, they contain salient content. By salient content, I mean that it contains a pattern that can be matched with this second order derivative. Okay? And once you pick that one, and then you do some calculation of the local histogram. That goes to the histogram of the gradient, the Hawk. Okay? Then you have a code word to describe that location. So instead of looking at the entire image, you only have a few points that you feel they are important. Okay? And at every point, you have a vector. That vector comes from the histogram of its gradients. So that will encode the image using a few vectors. So that's the feature extraction. Okay, so a little bit details about the Sift operation. So you can vary the radius of this Gaussian, and you can locate the radius by finding the maximum response. So I'm going to talk about that later, okay? But what is a Gaussian? Well, the Gaussian has this form. You have a 2D Gaussian. It has exponential of your coordinate, and then you have a radius sigma square. So that's the Gaussian equation. Now, one very, very interesting thing about this Gaussian is this equation. This is the key equation of the Sift transform. So if you take a Gaussian, and then let's say your radius is k times sigma. Okay? Now, keep this here, and then on the right-hand side, you subtract it from x evaluated at sigma. You take this difference. So what you're doing is that you have a big Gaussian, okay, k times sigma, that's a fat Gaussian. You subtract from a narrow Gaussian, okay? So fat Gaussian minus a fat Gaussian minus a narrow Gaussian. So what will happen? Well, you can do the math in your brain, okay? But what will happen is this. It will become something like that. Okay? What does it look like? Well, it looks like this. It's like a second order Gaussian. This is what has been proven by David Low. So he showed that when you take the difference between these two, you actually get something like this. And on the right-hand side of this equation is approximately equal to k minus 1 times sigma square. This is the Laplacian of the Gaussian. Okay, so that is taking the second order derivative of the Gaussian. So you can get this shape. So you say, okay, why do I want to do this calculation? This calculation says that if I can build a pyramid, and then if I can, once I do this pyramid, okay, in this pyramid, I will have this Gaussian, I will convolve my image with all these Gaussians. So at this layer, I'm going to convolve with sigma. The other layer, I'm going to convolve with 2 sigma, 3 sigma, and so on. If I ever want to extract the second order Gaussian response, I just need to take the difference between two layers. Okay, pick a pair of the difference, and then you can calculate the second order response. right? So that's extremely convenient. Rather than doing first constructing this and then convolving the image, you just convolve the image at all these scales and then take the difference. It's a lot faster. Okay, so this is one very, very interesting aspect of the Sift. Okay, so now this picture should be easy to understand. Let's say you have an edge image, and I really want to capture the location of the edge. How do? I send this first order Gaussian into the signal, and then I get a zero response because this is +1, this is -1. So when I try to convolve with that, I get 0, 0, 0 until I hit this point. Then suddenly I get a very, very big response. And then afterwards I get 0. So by doing this convolution, I will be able to locate the maximum edge location. Right? Okay. So now, if you do this with the second order Gaussian, then what you can find is that you will get this edge response. Right? So you'll get a +1 and -1 response. So this is what you will obtain by doing a second order Gaussian on an edge. However, the typical problem that you will encounter in computer vision is not an edge, because the edge is never a very important, it's an important feature, but that is usually not the salient object. The object usually it will be certain width, you have certain size, and then it has something. Think about there's a flower, and then you never just have one side of the flower. You always have the entire flower, right? So you have a disk. So let's say this is your underlying signal. And then if you try to filter the signal with your second order Gaussian, if the size of this object is too big, you will just get these two responses. Okay. However, as it becomes smaller and smaller, smaller and smaller, okay, so as the object becomes smaller and it matches with the radius of your Gaussian, you will suddenly get what? Well, you will suddenly get a very, very strong response. Okay? So here's the thing. If I want to detect an object of size, this size, okay, what should I do? Well, I should set my sigma, my second order Gaussian, the radius, also as something related to sigma, and then I do this filtering, then according to this picture, I will be able to get a maximum response. If my scale does not match with the scale of the object, then I will either get this or I will just miss it. Right? Is it clear? Right? Because if it's too big, then I will get this. If it is too small, I will just miss the entire thing. Right? So only at the right size, I will get a maximum response. And so this is why it's called it's related to this a scale issue, right? Because you want to find the size, the right size of blob to extract. So here is a pyramid diagram that I also extract from this paper. So what they do is that in the Sift diagram, so they first take the image and then they cut it into different layers. In each layer, okay, so in each layer you have multiple octaves. In each octave there are multiple layers. In each layer, it will be a Gaussian of different case. Okay? And then you take the difference at different Gaussian, you take a different pair. That would be called the difference of Gaussians. And that's actually the response of the second order derivative. And then across these layers, you are going to look for the response that has the maximum value. Then you know that, okay, that the important feature is actually located at this layer, this location. Okay. The reason why you need a pyramid is that sometimes your size is big, sometimes your size is small. If you have a big size and then you have a finite set of filter responses, what do? Of course, you downsample the image to make it smaller so that it will fit the set of filters that you choose. Okay. So this is for multi-scale analysis, but the basic principle can be understood in one layer. So what is the output of this Sift transform? Here is an image, okay? So you have this image, and then the Sift was going to extract features for you. In this particular example, I don't know how they set up the parameter, but you can see that they are really extracting places that this program thinks that's important. Okay, and then once you have identified the locations, then you can use it for multiple purposes. Here is one application where you have a pair of images. They are taken at probably different time, okay, at a different angle. And so you want to register them. So you want to say this pixel, okay, this region actually matches with that region, here matches there. Then once you have identified these key locations, then you can try to set up the correspondence. Okay, then what else can you do? Well, even with only one image, what you can do is that you can say, here is my image, and then here are the salient locations. For each salient location, I'm going to find the feature vector to describe them. So now instead of using how many pixels here, maybe a million pixels here, I just need to have a few vectors to describe this image. Okay, so that goes to the last thing with a Sift is called the histogram of oriented gradient, which is about how do you encode a region by its gradients. Okay, so let's say you have already picked a region. You say that I run the Sift method, and then it says that it is an important region. Then you go to here, and then you look at the local gradients. Now, how do you calculate the local gradient? That's also very simple. You take a 1 minus 1 filter, convolve it once, then you can get the finite difference approximation to the gradient. So you can get the horizontal gradient, you get a vertical gradient, and then they will give you a vector like this. So for every pair of two numbers, you will get a vector. Then in this region, you have a lot of vectors. So how do you do? Well, you can plot a histogram. You can plot a histogram, and then the histogram will have the x-axis being the angle. Now, there's another part which is the magnitude. Okay, here this diagram doesn't show you the magnitude, but I can point you to another reference that I should show you how do they merge both the angle and also the magnitude into just one histogram. And the idea is very simple. You look at you plot them out, and then you start to put the vectors into the right positions of this histogram. And once you put them into a histogram like this, this is just measuring the angle, right? So let's just focus on the angle histogram. That's already a code word, okay? So you're already encoding this entire block of gradients using a very simple histogram. So why is it simple? Because how many bins are here? 1, 2, 3, 4, 5, 6, 7, 8. You only need 8 numbers to describe this entire block of images. And with only 2 additional numbers, which are the x and y coordinates, you can describe this entire image. Right? So you say this image has these salient locations. For each location, it has a feature vector like this. And then that would be the description of the image. So you turn from a high-dimensional image, which is a high-dimensional vector. You can concentrate them into just a few of these small histograms. So that's called a feature extraction.